Welcome back. So we're on to greatest common divisor, or greatest common factor, as you might hear it referred to. I think this is probably going to be a pretty popular section because this is the topic that gets talked about a lot. And it can be very useful and very important going forward into algebra. So what is the greatest common factor? Well, we learned about the least common multiple. And so it kind of sounds like it's the opposite of that, and it's exactly the opposite of that. So we know that we know what a divisor is now. We learned about that in the last section. And a common divisor is a divisor in which is a divisor for two or more different integers. So if a number is a divisor of both a and b, then that's going to be a common divisor. We also can call that a common factor. When we do the prime factorization and we factor a number, we use the term factor, and it's the same thing. So the largest of these, so if we look at all of the common factors or common divisors, then the largest one is going to be the greatest common divisor, or greatest common factor, or GCF, or GCD. You might hear all these different terms, and it's all the same thing. So here's an example. So the divisors of 30 are 1 and 30, 2 and 2 and 15 should have been in here. 2 and 15, 3 and 10, 5 and 6. Those are the divisors of 30. So the divisors of 96 are going to be 1 and 96, 2 and 48, 3 and 32, 4 and 24, 6 and 16, and 8 and 12. All right, so what's the greatest of these? Let's see. So 96, no. 48, no. 32, no. 24, no. 16, no. 12, no. 8, no. But we have 6. So 6 is a common divisor. What else do we have? We have 3, 2, and 1 are also common divisors, but the greatest common divisor would be 6. All right, so the reason why this could be really useful for simplifying fractions is, let's say we had a fraction that's 30 over 96. We might not know what the GCF is, so we might just say, well, I know that these are both even numbers, so we can simplify this to 15 over 48, and then say, oh, actually these are both divisible by 3, and then it becomes 5 over 16, I believe. So that's two steps. But if we know the GCF, we know that the GCF is 6. That means these are both divisible by 6, and we'll go on this side here. So 30 divided by 6 would be 5, and 96 divided by 6 would be 16. So we can just do that in one step if you happen to know what the GCF is. All right, so jumping into this for problem 3.38. First of all, we're going to list the positive divisors of 18. Well, we know we have 1 and 18. 1 and 18. We have 2 and 9. And then we'll have 3. I'm going to pull up my cheat sheet over here, make sure I don't miss any. Yeah, we have 3 and 6. 3 times 6 would be 18. And I think that's all of them. Yeah, so that's for 18. How about 24? So for 24, we have 1 and 24. We have 2 and 12. 3 and 8. 4 and 6. And I think that's all of them. Okay, so list the positive common divisors. All right, so we have 1. We have 2. 3. Not 4, but we have 6. Let's see, what else we have? Not 9, not 18, so I think that's all of them. 1, 2, 3, and 6. All right. So D, what is the greatest common divisor? Well, the largest one of those is going to be 6. All right. So let's find the prime factorization for each of the positive divisors of 24. Compare these to the prime factorization to the prime factorization of 24. Do you notice anything interesting? Okay, so the positive divisors of 24, if we want to go back and look, or if you just remember, it's going to be 1, 2, 3, 4, and 4 times 6. We have 8 times 3, 12 times 2, and then 24 times 1. All right, so those are the common divisors. So the prime factorization for 1 is just 1. For 2 is just 2, we can say 2 to the 1. For 3, 3 is also prime, so 3 to the 1. 4 is going to be 2 squared. 6 is going to be 2 to the 1 times 3 to the 1. 8 is going to be 2 cubed. And 12, let's see, so if we have 12, let's see, that's 6 and 2 and 3 and 2. So looks like we have 2 squared times 3. And 24, we have 2 and 12, and we already know 12, so it's just another 2 there. So it's going to be 2 cubed. 2 cubed times 3 to the 1. I'll add 1s to these. Okay, so those are the prime factorizations of 24 and all of the divisors of 24. So do you notice anything interesting? Well, okay, so here is the prime factorization of 24. So let's compare all the other ones to this. So 2 cubed times 3 to the 1. So one thing that I do notice is that all of these only have, except for one, only have 2s and 3s. And also, there's nothing that has a power of 2 that's higher than 3. So this is 2 cubed, and the highest of all of these is 2 cubed here. There's nothing that goes over 2 cubed. So even though there are numbers here that are larger than 8, that larger than 2 cubed, it doesn't ever go to 2 to the 4th. We just have extra 3s at that point, less 2s, more 3s, and we'll never get more 2s or more 3s than we do for our main number that we're finding divisors for. So that's something to keep in mind going forward. All right, so this gives us the prime factorization for 1944. And below are 3 numbers and their prime factorizations. In each part, use the prime factorization of the number to determine if the number is a divisor of 1944. So I think we did the same thing for the divisors section, and also for the multiples section, very similar, where we compare the prime factorizations with this prime factorization to see if we can extract out some of this prime factorization into this prime factorization. So indeed, it looks like we can have up to 2 cubed, and we have 2 squared. And we can have up to 3 to the 5th, and we have 3 cubed. So it looks like this is indeed a multiple or a divisor of 1944. And if we were to do some division, we would find out that it would be 18 times 108 would give us 1944. All right, so 108 is a multiple or a divisor. You can kind of say either one. They're both true. They don't mean the same thing, but they are both true in this case. That 108 is a multiple, or 1944 is a multiple of 108. 108 is a divisor of 1944. So it kind of just which way you are thinking about it. I might have said 108 is a multiple. I misspoke. 1944 is a multiple of 108. All right, how about this next one? So let's see. We have 2 3s. That's okay. That's good. We can have 2 3s, but we can't have any 5s. There's no 5s here. So this is not a divisor. And 1944 is not a multiple of 45. Okay, how about 2 to the 4th? Oh, can't do that. So that is not a divisor either. So suppose we have 2 positive integers. How can we tell from the prime factorization whether or not m is a divisor of n? Well, just like that. If we can pull out those powers from our main number that we're looking at, then it will be a divisor. If not, if we can't do it, it's not a divisor. Okay, how can we use prime factorization of 360 and 48 to find the GCD? All right, so let's go ahead and let me just write out the prime factorization for you to save some time. But feel free to do it on your own if you wanted to practice your prime factorization. But for 360, the prime factorization of this is going to be 2 cubed times 3 squared times 5. Okay, and 48 is going to be 2 to the 4th times 3 to the 1. We'll add to the 1. I don't know if you like adding to the first power or not. Sometimes I don't really like doing it, but just kind of for for instructional purposes only, I'll add this in. But in normal practice, when in your future of your math career, you likely will generally not include these to the first powers. I'm just kind of showing a point that this indeed is only to the first power, and there is no higher power there. Okay, so now how can we use this to find the GCD? All right, well, similar to how we did this for multiples, it's a very similar thing. But we want to find the largest, the largest amount we can make common of these two. So for our base of 2, what's the largest power we can extract out? And that would be 2 cubed. Because they both have a 2 cubed in common. How about our 3s? What's the largest 3s that we could have? And that's going to be 3 to the 1. Because we can't do 3 squared, because then that would not be a multiple of 48. Or it would not be a divisor of 48. Yeah, would not be a divisor of 48, because this is going to be lower than 48. Okay, so how about 5s? Well, 48 doesn't have any 5s, so we can't have any 5s, so that we are done. And so what's this number going to be? It's going to be 8 times 3, which is 24. So 24 is going to be the greatest common factor, or greatest common divisor, or GCD, or GCF, whatever you want to call it, is going to be 24. And if we were to divide both 360 and 48 by 24, then they should both work out. And again, if we had a fraction that was like 48 over 360, just looking at this, you might not know what the GCF is, and you might not know the fastest way to simplify this fraction. You might keep on doing divided by 2, divided by 2, divided by 2, and that's okay if you kind of just want to shortcut this and simplify it as fast as you can. But if you happen to already know the greatest common factor or greatest common divisor, you would know that you can divide both the numerator and the denominator by 24. And I know we haven't gotten into fractions yet. We'll do that next chapter, but this would end up being 2 over, so what is 360 divided by 24? This goes in 10 times to be 240. This would leave us with 1, 2, 0. And let's see, so that would be, I believe, 5. That'd be 20, 10, 11, 12. Yep. So that'd be 15. 2 over 15 would be our simplified fraction in one step. Okay, so compute each of these. So greatest common divisor, and we could do this again with our prime factorization. So prime factorization of, we're probably gonna be using up a lot of room here. So let me just start up here. So 27 is going to be equal to, let me cheat here and pull out these prime factorizations. 27 is just gonna be 3 cubed. 3 times 3 is 9, times 3 is 27. 39 is going to be 3 to the 1 times 13 to the 1. Okay, and so the GCD would be what's the largest common power for 3? It's going to be 3 to the 1, and no 13. So the GCD for this is just going to be 3. Okay, so next one we have 100. Is going to be equal to, well, we know it's going to be 10 squared is 100, which would mean it would be 2 squared times 5 squared. Right? 2 squared times 5 squared. Okay, and 63 would be 3 squared times 7 squared, 7 to the 1. Ooh, okay, interesting. Well, not finding anything in common here, so the GCD, does that mean that there is no GCD? There's always going to be a GCD, because remember, when you list out the factors for 100, what's the very first factor? 1 times 100. And what's the very first factor for 63? 1 times 63. So there will always be 1 as a GCD. So if there's no higher GCD, then 1 is going to be the greatest of your common divisors. There will always be 1 as a common divider, and sometimes 1 will be the greatest of them. Okay, so Well, let's see here. This is already prime factorized for us, so let's just find what's in common. So the largest base of 2, nothing. Largest base of 5, looks like 5 squared. And largest with base 11 would be 11 to the 1. And let's see, yeah, no 3s over here, so I think that's going to be it. So this would be 25 times 11. Who remembers our 11s trick? 275. Remember, so if you didn't watch the video that I talked about the 11s trick, what you can do when you multiply by 11, especially when you have a 2-digit number, is in your product here, the first number is going to be the first number. The last number is going to be the last number. You see 2 is first, 5 is last. And then the middle number is going to be the sum of these two numbers. You add them up, 2 plus 5 is 7. So 2 and then 7 and then 5, and that's the product of 25 times 11. Super neat trick, I love that trick. All right, so then GCD of 72, 240, and 288. All right, so for 72, we have 2 cubed times 3 squared. 240 is 2 to the 4th times 3 to the 1 times 5 to the 1. And 288 is 2 to the 5th times 3 squared. All right, so what do we have in common with all three of these? Let's see. For 2's, our largest base of 2, we have 2 cubed. Not the largest, the smallest. The largest that we can do that would be common is what I meant to say. All right, so the largest that would be common to all three would be 3 to the 1. And we don't have a 5 that would be common to all three. So it looks like this is going to be 8 times 3, which would be 24. All right, so 24 would be the greatest common divisor for these three numbers. All right, so the GCD of 2 times 500 and 2 times 300 equal to 2 times the GCD of 500 and 300. All right, so for our prime factorization for 500, that's going to be 2 squared. We did a very similar problem to this in our LCM, our least common multiple section. And 5 cubed. 300 would be 2 squared times 3 to the 1 times 5 squared. All right, so what do we have common for these? We have a 2 squared common. We have no 3's common. And we have 2 5's common. 5 squared common. That's going to be 4 times 25, which we know is 100. And that makes sense if you just look at these two numbers. And then 100 seems like it would be a common factor. So that would be the greatest common factor for 500 and 300. So 2 times that would be 200. Okay, so is that going to be equal to the GCD of 1,000 and 600? Let's see. So 2 times 500 would just be another 2. So 1,000 would be 2 times this. So 2 cubed times 5 cubed. And for 600, well, that would be 2 times 300. So another factor of 2. That would be 2 cubed times 3 to the 1 times 5 squared. So then what do these have in common? And we have 2 cubed now. Still no common 3's, and 5 squared. So this one is going to be 8 times 25, which would be 200. All right, so these are the same, so that checks out. They are equal. So let A and B be positive integers, must we have GCD 2 times A, 2 times B equal to 2 times the GCD of A and B? Well, just like we did for our LCM, it's going to be the same thing. And we can show that by knowing that the factors, or like whatever the prime factorization is for A, when we have 2 times the prime factorization of A, it's just going to add another factor of 2. So then when we find what's common, then what's common to both of them will be an extra factor of 2, because they're multiplying both by 2, so they're both going to have the extra factor of 2. So of course it will be 2 times the GCD of A and B. So that is true. Okay, and so same thing for this. This is going to be having, this wouldn't be, well, so if we prime factorize 15, that would be 3 and 5, right? 3 times 5. So multiplying in a 3 and a 5 into whatever A is and to whatever B is, well, then when we find what's common to them, then it's going to have an extra factor of 3 and an extra factor of 5. So it's going to have an extra 15 times whatever the GCD of A and B is. So that also checks out. So now let's go ahead and compute this GCD. So let's see. So we know that 606060 is the same thing as saying 10 times 6. And so let's do GCD, this function. And then the other is going to be 10 times 7. Okay, and then we know we can factor this out. So then we have 10 times the GCD of 6 and 7. And what's the greatest common divisor of 6 and 7? Well, that's going to be 1. So it's going to be 10 times 1 would, of course, be 10 would be our answer. How do we find that 1 is our greatest common divisor? You can kind of just tell by looking at it, because what are the factors of 6 going to be? 1, 2, 3, and 6. 7 is the prime, so there are no 7s in the prime factorization of 6, so they're not going to have anything other than 1 as a common divisor. So that's how I did that so fast. All right. So 3.44. Every bag of candy in the grab bag candy store has the same number of candies. Tony and Kaya each grabbed some bags of candies. Tony gets a total of 7 candies, and Kaya gets a total of 42 candies. What's the smallest possible number of bags Tony could have grabbed? Okay, so let's see. Grab some bags of candy. Tony gets that and that. So, right. So each bag has an equal number of candies in them. So in order to grab a bunch of bags that equal 70, well, each bag has to have some divisor of 70 in each bag. And it also has to be a divisor of 42. So there can't be 70 candies in each bag, for example. So the possibility that Tony only got 1 bag that happened to have 70 candies isn't possible, because Kaya only got 42. So even if she only got 1 bag, she'd have more than 70. Hopefully that sort of makes sense. So we have the number of bags, I'll say B, times the number of candy in each bag, I'll say that's C. For Tony, this is going to equal 70. Here, so we'll do bags for Tony, and then we'll say bags for what's the other one's name? Kaya. Bags for Kaya times C is going to equal 42. And we know that C is going to be the same for each of these. Okay, so let's go find out what the divisors for 70 are. We can either do this with prime factorization, or we can list out the the divisors or the factors of 70. Let's go ahead and do the prime factorization. We've been doing that more. So 70 is going to be equal to 2 to the 1 times 5 to the 1 times 7 to the 1. 5 times 7 is 35, times 2 is 70. How about 42? For 42, we have 2 to the 1 times 3 to the 1 times 7 to the 1. 7 times 3 is 21, times 2 is 42. Okay, so what do we have in common? We have a 2 to the 1 times 7 to the 1, which is going to be 14. So there has to be, well, I wouldn't say there doesn't have to be 14 candies per bag, because there could be 1 candy per bag, right? And maybe Tony got 70 bags and Kaya got 42 bags. But the smallest number of possible bags would be, well, the largest number of candies that could be in each bag would be 14. So that's not going to be our answer yet, but there could be 14 candies per bag. And if that is the case, that's the largest number that could be in each bag, then what's the smallest possible of numbers Tony could have gotten? Well, that would be 70, which is the total candy that Tony has, divided by 14. And how many would that be? Would that be 5? Let's see. Yep, that would be 70. So 5 bags would be the smallest number of bags that Tony could have grabbed. The largest number of bags Tony could have grabbed would be 70 if each bag had 1 candy in it. Hopefully that makes sense. All right, so find the GCD of 4 and 9 and the LCM of 4 and 9. Okay, so going back to remembering how we did the least common multiple. So first of all, let's go ahead and do the prime factorization for these. That'll make both of those a little bit easier. So we know that 4 is equal to 2 squared, and 9 is equal to 3 squared. Okay, so to do our GCD would be, well, there's no common 2s and there's no common 3s, so the GCD has to be 1. What about our LCM? Well, for our LCM, if you remember, we don't have to have them in each. We take the largest of everything. So our LCM would be, our largest power of 2 would be our only power of 2, would be 2 squared. And our largest power of 3, which is our only base 3, would be 3 squared. So our LCM would be 4 times 9, which would be 36. That would be our least common multiple. There's no multiples lower than 36 with 4 and 9. So remember, the multiples of 4 are between 4, 8, 12, 16, 20, 24, and so on. 9 is going to be 9, 18, 27, 36. And then so 36 is where they meet for the first time. If you remember, that's what LCM means. All right, so let's see, find the GCD of 10 and 27 and the LCM of 10 and 27. Okay, so 10 is going to be 2. 10 is equal to 2 to the 1 times 5 to the 1. And 27, I believe that's going to be 3 squared, or 3 cubed, right? 3 cubed, yeah. Okay, so same thing as before. So our GCD is going to be 1, because there's no common basis here. Our LCM is going to be 2 times 5 times 3 cubed, which is 27. So let's just say 10 times 27, which would be, LCM would be 270. And again, so if we counted our multiples of 10, 20, 30, 40, 50, and then 27, and then 54, and then so on, the first time that they would meet would be at 270. All right, so let A and B be positive integers such that the GCD of A and B is equal to 1. Explain why the LCM is A and B. Well, okay, so what's common between these two, where the GCD was 1 and the LCM ended up being multiplying the two numbers together, right? 4 times 9 is 36. 10 times 27 is 270, and the GCD is 1. So why is it the case that both of those were the case? And will it always be the case? Well, the reason why the GCD was 1 is because they didn't have any common bases. 4 only had a base of 2, 9 only had a base of 3. There were no common bases. So that the GCD had to be 1 because they had nothing in common. For the LCM, well, there was nothing that, nothing higher that we could have taken. So if we had a, let's say, times 2 here, 2 to the 1 here, then we could have taken this 2 to the 1 instead of the 2 to the 2, but we didn't have anything common, so we had to take the full amount for everything, which ended up being multiplying them both because they had no common bases. Let me see if I said that right. Okay, if A and B are relatively prime, then their prime factorizations cannot share any prime factors. So the prime factorization of LCM A and B is the product of the prime factorization A and B. This means that LCM AB is equal to AB. Yeah, I'll come back to this if I have a better explanation. Hopefully that made sense. If it didn't make sense, let me know, and I'll re-explain that in a better way. Okay, so must a number that is a multiple of 4 and 9 be a multiple of 36? All right, so if it's a multiple of 4 and of 9, must also be a multiple of 36. Yeah, well, because the least common multiple of 4 and 9 is 36, that's what we found out in the last slide, then the only common multiples, if you remember when we talked about least common multiple, we know that every common multiple of two numbers or more numbers is going to start at the least common multiple and then happen at every iteration of that least common multiple. It'll happen again that least common multiple number of times. What I mean by that, so if 36 is the least common multiple, then the next common multiple will be 36 after that, so it would be 72. So the common multiples of 4 and 9 will start at 36. That's going to be the least common multiple, and then the next one will be, did not write that very well, 72 would be the next common multiple. There would be no common multiples until 72. And then after that, it would be 108 would be the next common multiple. So they're always going to be 36 apart. So because they're always going to be 36 apart, let's see, a number that is a multiple of 4 and 9, so any of these multiples of 4 and 9 will also be a multiple of 36, right? This is 36 times 2, 36 times 3, and so on. So yes. Must a number that is a multiple of 3 and of 12 be a multiple of 36? Well, let's see. So the multiples of 3 are 3, 6, 9, 12, and so on. Multiples of 12 are 12, 24, and so on. So the answer is no. The least common multiple of 3 and 12 is going to be 12 in this case. 3, 6, 9, and 12. So that's the first multiple that's going to be common to both 3 and 12. So because the LCM is 12, then the common multiples is going to be 12, and then 24, and then 36. And 12 and 24, of course, are not multiples of 36. Multiples have to be at least that number or higher. So 12 and 24 are not going to be multiples of 36. So this is no. Okay, and find a digit A such that 5, 9, 7, A6 is a multiple of 36. Okay, so this one's interesting. And so we haven't really discussed this yet, but in order for it to be a multiple of 36, we know that it has to be both a multiple of 4 and 9. So we can do our divisibility test for 4 and 9 and make this such that it will be a multiple of both 4 and 9. So how do we make it a multiple of 4? Well, a multiple of 4 would be the last two digits have to be a multiple of 4. So actually, let's go ahead and make it a multiple of 9 first, because that's going to be a little bit more strict. So multiples of 9, if you remember, you add up all the digits, and that has to be a multiple of 9. So let's go ahead and do that. So we have 5 plus 9 is 14, plus 6 is 20, so we have 27. 27 is already a multiple of 9. So A could either equal 0 or 9. That's the only two options. Okay, so if A is 0, then the last two digits would be 0, 6, which is not a multiple of 4, which means A has to equal 9. Now let's make sure that 96 is a multiple of 4. Let's see, we'll go in there 20 times. That's 80, 16, and 4, so 24. So yep, that is the case. So A would be 9. All right, and the reason why we were able to get there is because we know that that 36 is a multiple of 4 and 9. So we can just use a divisibility test for 4 and 9 instead of trying to do it for 36. And that's it. So that's it for 3.7. Go ahead and do your 3.7 exercises. And that's actually it for chapter 3 as a whole, too. So the next section is going to be 3.8. And I recommend going through 3.8 as a summary for the entire chapter. And then go ahead and do your the review and challenge problems. I know there's a lot of them for these end of chapter review questions, but very helpful to make sure that we got this down really well. Because we're going into fractions for chapter 4, and knowing these LCMs and GCDs, GCFs is going to be really helpful for being able to get through fractions easier and faster. So until then, I will see you for chapter 4.